Okay, this is I think on our over the mod plan. This should have been day 5, but we're doing it after day 3. So we're going a little bit out of order because we learned about the coefficient of kinetic and static friction on day 3. So it's a good day to do the experiment on day 4 following that. So here we are, and we're going to do a lab. And I'll do my best to explain the lab, and without being there and actually showing you, I'll give it a try anyway. Find the coefficient of sliding friction for wood on a board. That will be your objective. And when it says sliding friction, we call that kinetic. So, kinetic friction. So we're looking for mu sub k in this exercise, at least the first part. So the directions will go in this way. It'll say find the weight of your frictional block. So first of all, your friction block is just going to be a block that I'm going to hand out, or Mr. DeBloom will hand out. And it's a block of wood, and it has a hook on one end so that we can work with it better. So there's a block of wood for your group. And the next step, you have to record the weight of the frictional block in this table. So you're going to have to borrow from chemistry one of these triple beam balance, and you're going to put the block on here. And it's very important to calibrate this area right here before you start. Make sure if all of these settings are on 0, you've slid these little bars over and they're at 0, that the balance is completely balanced at the 0 line. And you can mess with some measurements. You can mess with some of, I think it's this knob right here, in order to get it to balance exactly. So you want to calibrate it, make sure that you're getting a very accurate mass from it. So you're going to use that. And the first thing you're going to do then is find the mass of this block of wood, and you'll be charting that. So say the block of wood is, I'm just kind of guesstimating from home, say the mass of the wood turns out to be 0.09 kilograms. So the block of the wood in kilograms. So notice we're asked to do newtons. So you're probably going to get grams on the actual scale, so you'll change it to kilograms. And let's say when you do that, let's say it's actually, I think I might have a better estimate here. So this is not one where you have to take notes on for actual evaluation, but you do need to take enough notes to know what to do. So say we have a 0.59 kilogram block. I think that's more accurate. And say it's time to find it in newtons, we'll have to multiply times 9.8, and that's meters per second squared. So we'll have kilograms times meters per second squared, which is what a newton is. So we'll get something like 5.8 newtons. And you can decide how many sig figs to use. Actually, if we're using 9.8, we can actually use another digit there. If we're actually able to measure this to 3 significant digits, we'll go ahead and use 3 and the 9.8. The next significant digit in the gravity constant is 1. So you might be able to add another digit to this. I have 5.8, maybe you have 5.80. You can use 3 sig figs here. So make sure you're thinking about that. So under the block weight, you're going to find the mass on the scale and multiply, put it in kilograms and multiply by 9.8 and get some measure of the block weight in newtons. Then the next direction is attach the force scale to the block. So let me show you what that is. The force, attach the force scale I call it a spring scale. It's this thing. And before you work with that, it also has to be calibrated. Right here, there's a little crossbar right there. And that should be crossing right at 0 when it's not pulling anything. And you'll see how to calibrate that. You're going to pull up or down on one of these little tabs here. So you'll be able to calibrate that as well. So you want to make sure you're starting in 0. So you're going to take that spring scale. Here's my drawing of the spring scale. You're going to hook it to the hooky thing coming out of the block. And you're going to pull it across the table that you're working on. And one group would actually use the board up in the corner. So Mr. Bloom, you can pick who uses the board. And everyone else can use their table as a board. So you're going to pull it along this table until you see that the block is, you don't want the reading right when you start, because we're trying to find mu sub k. So we want this block to be moving along. It's not right when it starts. So there should be more force to get it started. But we want to see what is the Newton scale that you're reading when you're pulling this along and it is moving at a constant rate. So we're going to attach the force scale to the frictional block and pull the scale horizontally. Now some students make the mistake of pulling upwards. We want the angle between the hooky thing and the spring scale to be 0. So we want to be pulling along horizontally parallel to the board or table. So as you attach the force scale to the friction block and pull it horizontally at a steady rate. So we don't want you to be jerking or anything. We want it to get it started and pull it at a steady rate. Once you get it moving at a steady rate, a constant rate, read the Newton scales. So that will be called the friction force. So this exercise will find the friction force. It will be read in newtons. I think there's 2 scales on those. I think grams and newtons, something like that. You want the Newton scale. Do you want to use that? So that'll come down in this chart. And let's say that we get a frictional force of 0.8. That will go in this force of friction here, and I think it'll say to measure it in newtons. So that's the actual force that was needed we had to overcome the force of friction with this force in order to keep the block moving at a constant rate. All right, so now you'll notice on the first trial that we are not adding any additional mass or weight, so there should be zeros already in your chart for that. And so you can go ahead and figure out what force normal is. By force normal, you recall, is going to be mg. When we're on a flat surface, force normal is the positive, the positive reaction to weight downward. So force normal this is for the block. So force normal is going to be the same as, this was the weight downward. Force normal, unless your block is crashing through your wood or your table, which I'm assuming it's not, that means force normal is supporting it. So at 5.8 newtons was the weight of the block downward, and so force normal is going to be 5.8 newtons upward. So we could put in a negative sign to emphasize that. So the weight is downward and force normal is upward. All right, so finally we are going to find the frictional coefficient. We know this relationship to be true, and I think I wrote it on the lab. Force friction is mu sub k force normal. So we have the force of friction from this column, and we have the force normal from this column. So we're going to divide both sides by force normal. So you'll have this number divided by this number, and it will get you the frictional coefficient. So that will be a measure, and we're expecting a number that is below 1, like 0.25 or something. I don't know what that divided by that is, but you will find out, and you're not going to use my made-up numbers, you're going to use your numbers. But we're expecting a number like that below 1, and they should be, and this is a measure of how much bumpiness and catching and threading that the surface of the block has with the surface of the table. And so this is helps measure how much resistance or friction there is between the two surfaces. All right, and then you'll have 5 trials to do, and I'll discuss the second trial, and you'll know what to do for the rest of the trials. And you'll go back to the block weight again, which is going to be the same for every trial. So the block weight, if it was 5.8 here, it's going to be 5.8. The block isn't going to change in its weight between trials. But then you're going to add some additional mass. So you're going to go to your set of masses. So there's plenty of those around the cabinet. They're either on top of the cabinet or in the cabinet. And you're going to pick an additional mass. Suppose that you take an additional mass of 200, I think they're in grams, so that would be 0.2 kilograms. So we're going to work in kilograms, and you're going to have to change that 0.2 kilograms to weight. So you're going to go 0.2 times 9.8, and that will get you 1.96 if you're using. This is, even though it looks like it's one significant digit, these mass weights are correct to as many digits as you want to use. So it's exactly 200 grams, so you can think of it as a decimal there. So we can use 9.81 and get the third there. And so when we do that, we are going to get something like 196, I believe. So 196 is the number of additional weight that we're putting on. So you're going to actually sit that 200 gram mass on top of the block. So up here, when you have this step here with the spring scale, you're going to put a mass right here. And you're going to do it again. So you're going to pull the spring scale horizontal to the table. You're going to read the newtons that it uses, and that's going to go under force of friction that had to be overcome to keep the mass moving at a constant velocity. So let's say when we added 0.2 kilograms, let's say the spring scale read, I don't know, it was 0.8 here, suppose it went up to 1.2. So you want to fool with these spring scales. They're not the best, but you expect more when you have more mass, it's going to be a higher reading. So keep that in mind as you're trying to read the spring scale. So over here, we are going to have to calculate the normal force. So when we have the additional weight was 1.96, so the normal weight now is going to be the sum of what was this? 1.96 is the additional weight, and we're going to add these two because we still have the weight of the block. So 5.8 and 1.96 will give us something like the normal force is going to be, the weight is 5.8 plus 1.96, say 7.76, if we're allowed to work in 3 sig figs, if that's working out for you in reading the all the instruments. So you're reading them to 3 sig figs, you can use that. So say we're up to 7.76 newtons, and that's the normal force. I added these two, and I know that the weight downward is countered by force normal upward. So there's that. And the coefficient of friction is again calculated from this formula where we're looking for this, and we have force normal, which is in this column, and force of friction in this column. So we're going to divide this number by this number, and the idea is to come up with the same thing, but we will be slightly different as we are in lab. So then you'll continue to do that for trials 3, 4, and 5. And at the end you'll have several. Suppose you have 1.18 and you have 0.26, and they're all over the place, but in the end you're going to have 5 coefficients of friction for wood on wood, and this will be averaged. So say you've got 2, 1, so you're going to average all these 5 and come up with an average, and there's a little blank down under your chart for that average. Alright, so that part has to be done, and I want you to go as far as time allows you to do for the rest of the lab. So you'll see that you're going to do a similar thing on part 2. They asked you to turn the block on its side and do the same thing. So where we had the block in this direction, on part 2 they ask us to turn the block this direction. So it's going to be, instead of sliding on this wider part, it's going to be sliding on the very thin part here. So this is same procedure, and you'll see the chart looks the same. In fact, since we won't all be able to finish all of these, Mr. DeBloom, if you could assign one group to do this. Everyone does the first chart on the first page, but then split it up among the groups. One group can do this, and this is where you use your shoe on wood and come up with the frictional coefficient of a shoe on wood. And then another group can do, let's skip this one, so no one do that one. It has some math in it that we haven't covered yet. When we get to the inclined plane, we can come back and work on that one. And then another group could do the shoe on a wet board to see how it compares to a shoe on a dry board. Alright, so that is your goal for lab today, and I hope that explanation will clarify some things. So, carry on.